Says so many are joining now. So I have to every time I have to minimize it. That becomes an issue. Okay. Uh, so basically, we will be discussing about what are the basically the two types, important types, that is a two-stroke and four-stroke engine. We will discuss about some constructional details, and then we will be discussing about how they are working and correlate its working with the wall timing diagram, and then we'll go to cycles. So this is what is being planned for today. So let us start with. So basically, we have a two-stroke engine and a four-stroke engine. These are the two important engines what you have learned. So let us see in brief the constructional details of the two engines. So a four-stroke engine is something like this. So here you can see four-stroke engine, how it is. So it is a block diagram like arrangement. It is not actual engine arrangement. So you can see it is shown over here the inlet manifold through which the fresh air, if it is a diesel engine, and air fuel mixture if it is a petrol engine is coming. And this is your combustion chamber. And this is the path where the exhaust gases, that is the burned gases, are supposed to go outside. So this is called as an exhaust manifold. So this was your inlet manifold, and this is your exhaust manifold. Now in the inlet manifold we have here the inlet wall arrangement. So across the inlet wall the fresh air or the air fuel mixture is supposed to come in, and across the exhaust manifold it is supposed to go out. The burned gases are supposed to go out. This is your spark plug which is supposed to fire the mixture. In case of a SI engine, it will be there. Instead of this, it will be an injector if it is a diesel engine. Okay, that is going to be different. And this is your piston, this is your connecting rod, this is your crankshaft with the offset distance shown over here, which we call as the crank. And the part which is covering the crank and all is called as a crankcase. And the lower part where we have some oil is called as a sump. The upper part is called as a cylinder head. This part is called as a cylinder, and here the cover will be there. So tappet cover and everything will be there to here. So on the upper side of this particular wall there will be the rockers, and that covering that what we is called we have a tappet cover. So this is how a four-stroke engine is. So in brief, the constructional detail is something like this. Now, when you compare this to a two-stroke engine, it is something like this. So you in this particular diagram, you can see, this slide, you can clearly see the constructional difference. Okay. So here you can see this is a two-stroke engine, and this is the combustion chamber. Now, here this particular inlet manifold is here now. So the inlet manifold will be connected over here, and that means the air or the mixture is going to come in from here. Okay, and the exhaust manifold is here, which will be connected over here. Okay, so this is your exhaust port here, and this is your inlet wall connected to inlet manifold. Okay, so the inlet manifold, and we know that for a two-stroke engine, we supply the basically the air fuel mixture, and or that is if it is a petrol engine, and if it is a diesel engine, only air. So if it is a petrol engine, then you have to connect here the carburetor. So in this inlet manifold there will be carburetor. So the air will be coming in the carburetor, fuel will be coming in the carburetor, mixture will be prepared, and that mixture will be supplied to the crankcase of a two-stroke engine. Okay, so this is a crankcase engine. And this is a valve over here. There will be a valve over here. So whenever whenever this piston moves up, what happens here? Here there will be a negative pressure created, and this particular negative pressure will result in the opening of this particular reed valve. So this is a reed. Basically, it is something like a covering hole, a small flat plate covering a hole. It is called as a reed. Okay. So what happens is, suppose the reed is over here, reed valve is attached over here. Here the reed valve is attached. Now what happens? The hole is like this, and the on this this side, on the right side of this particular wall, there's going to be that flat plate covering the hole. Now, whenever the pressure on this side becomes lesser, this reed wall or this particular plate, whatever, is going to be pulled towards this side to some extent, and there will be gap between the hole and the plate, and we say it is open. Therefore, the gases can flow in. Okay, so this wall will be opening depending on the pressure over here. So whenever the pressure is negative over here, the wall is going to open. Whenever the pressure is going to be higher, more than atmospheric, what will happen? The pressure will be acting on this side, that is on that particular plate, and that will press the plate on the surface of the wall. Therefore, there will not be any gap between the plate and the hole, and therefore it will be closed. That means whenever there is a negative pressure over here, this is going to open and allow the things to come in, and whenever the pressure is higher over here, it is going to be pressed and it will be closed. So that is the function of the reed wall over here. Now, it is not only that this will be opening on the basis of only reed wall. So there are different types of walls which can be used. One of the wall I have just told you that it can be a reed wall. Now, what it means is again that here the pressure over in the crankcase is going to play a role in suction. So basically the suction, we are not talking of the suction of the combustion chamber, that is suction into the cylinder in the crankcase. So here the mixture will be initially coming in when this wall is open, and this will be accommodating in this particular region. So this will be filled until this is open. There will mixture, or so basically let us consider that is a petrol engine. So we will talk of a mixture. So the mixture will be coming, air fuel mixture will be coming in, and it will be occupying in this particular region. So not necessarily if it is a diesel engine, only air is going to come. Remember this thing. So here this area is now, this particular volume is now being occupied by the air fuel mixture, considering it is a petrol engine. And when this will happen, when the piston is moving up. Why this will happen? Because the piston has moved up and a negative pressure has been created. So negative pressure over here, sorry, a negative pressure over in this region, and positive pressure on the outside, that is atmospheric pressure. So here we have created a pressure lesser than atmospheric, and that is why the fluid, here the mixture is a fluid. Okay, so a fluid can be a gas or a liquid, it can be called as a fluid. So the fluid is now moving in this direction, that is through this particular inlet wall, it is going to come in and occupy this particular region. So this region is now filled with air fuel mixture. Now the piston will move up, reaches the top dead center, and when it is coming down, what is happening? When it is coming down, the mixture over here is going to be getting compressed. Correct? The pressure will go on increasing. Some stage will come when the pressure outside and inside will become equal. Once the pressure become equal, thereafter any movement of the piston in the downward direction will result in the pressure here to become positive, more than atmospheric. So there will be a tendency to move in this direction. But what happens? Due to the higher pressure inside the crankcase, this wall will get closed, and therefore the mixture is trapped over here. So inside the crankcase, the mixture is getting trapped. Now further, as the piston moves, the pressure goes on increasing, and it will become more and more positive pressure. Okay, so the pressure will build up inside the crankcase, and we know that when this is opening the transfer port, then there is a passage where it can flow. So this is your transfer port, and through the transfer port, the mixture is going to flow into the combustion chamber. So this is how when we in the previous lecture, when we discussed about the piston moving down and the piston moving down and the mixture will be flowing through the transfer port. But why it has to be flow? Because we know that as the piston is moving down, the pressure over here is becoming positive. Okay, so it is going to increase, and due to higher pressure over here, the gases will be having a tendency to flow. So whenever there is a gap over here, the mixture tends to flow into this particular region, and that is how the suction is happening. Okay, and we also have discussed projection on the upper side of the piston in a case of a two-stroke engine. We have discussed that there will be some projection, and we said that it is for deflecting the mixture. So here you can see this particular projection. So where you can see whenever this is coming over here, the gases will hit here and it will be moving in this direction. Okay, so it will be occupying this. So otherwise, what will happen if this is not there? If this is not there, this projection is not there. Whenever it is moving down, this port will get opened, and there is a tendency that the gases can flow directly. It will not occupy this region. It will have a tendency to directly go out. It will come in through the transfer port and go out through the exhaust port directly. It will not occupy this region. So in order to make it occupy this region, what we have done, we have provided a projection on the upper side of the piston. Okay, so this is I think we have discussed when we discussed in the previous lecture also, and when we discussed the piston, we have said that there is a projection on the upper side of the piston for generally used for a two-stroke engine. So this is the projection for that. So I hope the so then we have a piston over here. So this is your exhaust port, this is your transfer port, this is your piston, this is your connecting rod, this is your crankshaft. Then we have an inlet valve over here. This is a transfer port, this is spark plug, this is your combustion chamber. Okay, so this, I think everybody has understood the constructional difference between the two engines. So here this is a spark plug. Here is a spark plug if it is a two-stroke engine. Instead, if it will be an injector, if it is a diesel engine, so here it will be an injector if it is a diesel engine. Okay, spark plug if it is a SI engine. So depending on SI or CI, the spark plug is going to either it will be a spark plug or it will be a injector. So if it is a spark plug, it is going to fire and make the mixture to burn. If it is an injector, it is going to inject. And when this is going to happen? At the end of the compression stroke. Okay, so the piston is moving up and down, and your strokes are going to happen. So in a four-stroke engine, initially when this is moving down, the suction will happen. Then it is compression. Then it is working stroke or power stroke, and then we have an exhaust. Okay, so the piston will move here 4 times, 1, 2, 3, 4. And unlike here in a two-stroke engine, as the name indicates, 2 strokes, piston will be moving from TDC to BDC first to make the gases to flow out and new charge to come in, and then compress here, and at the end there will be a power stroke. So there are only 2 strokes will be there, 2 strokes of the piston, and during the 2 strokes here, the crankshaft is rotating once. Here during the 4 strokes, here the crankshaft is rotating twice to complete 1 cycle. So if as we discussed earlier, we said that if the engine is there having speed of or rotary speed of the engine is revolutions of the crankshaft is 1000 in case of a 4-stroke engine, how many power strokes will be there? 500 power strokes will be there. On the contrary, if the RPM of the engine in case of a 2-stroke engine is 1000, then how many power strokes will be there? There will be 1000 power strokes. So that is about the, see, this is every time I have to minimize and admit, so that becomes an issue. So okay, so we were discussing about the 2-stroke and 4-stroke engine construction. I hope everybody has understood the constructional details of a 2-stroke engine and a 4-stroke engine. Though we have discussed the parts earlier, we were not exactly knowing what is the basic difference between a constructional difference between a 2-stroke and a 4-stroke engine. So here in this particular slide, I think I have made it very clear what is the constructional difference between a 2-stroke and a 4-stroke engine. Okay, now moving ahead, now let us discuss the operation. So the operation, as we are knowing that the cycle is going to be complete in only 2 rotations of the crankshaft in case of a 2-stroke engine. So now let us consider the piston is moving from top dead center to bottom dead center. That means the piston is now at top dead center. So this is at top dead center. Now we know that what is happening at top dead center. When the piston is at top dead center, the mixture is here. Whatever has been earlier trapped in, from the when the piston was moving up is now getting compressed over here, and that particular compressed charge is compressed to the maximum extent, whatever is the requirement as per the design. And here now at this particular end of the compression stroke, the spark plug is going to fire. And when the spark plug is going to fire, there will be a spark generated, and The spark is going to burn the mixture over here, and the mixture is going to burn. And when mixture burns, the pressure inside the combustion chamber is going to increase, and that pressure is going to act on the head or crown of the piston, and this particular piston is going to move down. So now here we are saying the combustion is happening. Okay, so the combustion happens and the piston is going to move down. So we say the expansion stroke is happening, correct? So since the piston is moving down, we say the expansion stroke is happening. Now as it moves down from this, that is top dead center, towards here, until the piston reaches over here, till here it was the expansion stroke. So from TDC to here it is effective expansion stroke. But the instant when it moves further down from here, you can see the gap is opening here, the exhaust port is getting opened, okay, uncovered. And since the exhaust port is getting uncovered, the gases starts flowing out. So the exhaust gases are going to flow out through the exhaust port. Okay, so this is what happens. So what is this? This is a exhaust stroke happening. So here we said expansion stroke was happening. Here we are saying exhaust is also happening. Now further as the piston moves down, you can see the transfer port is also uncovered, and when the transfer port is uncovered, the mixture starts flowing in. Okay, so since the mixture is now flowing in, and due to this particular projection over here, it is getting diverted. Okay, so if this was not there, what will happen? This we know that earlier this particular is filled with the which gases? Burnt gases, exhaust gases, which was supposed to be exhausted. Now that means the exhaust gases are here, and if new gases are coming, and if this projection was not there, then this will start flowing out, while this region will be occupied by the burnt gases or exhaust gases from the previous cycle. Okay, so this particular burnt gases will not allow the fresh charge to move towards upward direction because they have a easy passage like flowing out like this. So whatever we are going to inlet, that will go directly, and here this gases will remain as it is. So what we have done, we have given the projection over here, and due to this projection, what happens? The incoming gases are now deflected towards the upper side. Now this goes and pushes the products of combustion from the earlier cycle, that is the burn gases, it is being pushed from the back side, and it will make this particular gases to flow out. So this particular process of that is pushing out the burned gases from the cylinder is, or it is called as flushing out. So flushing out this particular burned gases from the cylinder is called as scavenging. So this particular projection provided on the piston crown helps in the scavenging. Okay, so scavenging is the process of cleaning out or pushing out the burned gases from the combustion chamber towards the exhaust or to the atmosphere. Okay, so that is what you call as scavenging. Okay. So this is what the scavenging is happening, and since the scavenging is happening, we have here that is the projection here, and this particular projection will help in diverting the gases, incoming fresh gases, which is a air fuel mixture in case of a petrol engine, in such a manner that it is getting diverted towards the upper side. Okay, so this is getting upward, so it is moving upward, and it will push the gases present over here, and it will make this to exhaust gases or the burn gases to move out through the exhaust port. So this is what you call as the suction is happening. So simultaneously here the exhaust has started, here exhaust is being continued, but suction also has started. So when the suction is happening, air fuel mixture is coming in, and it is occupying the volume inside the combustion chamber. Okay, now further as it moves, it reaches BDC. So as it moves, it reaches bottom dead center. Okay, so as it moves down, you can see it is moving and it is reaching bottom dead center. So when the piston is reaching bottom dead center, what is the condition? Exhaust is open, so exhaust is going on. Transfer port is open, So the suction is going on, correct? And when it was moving from here to here, expansion has happened. So expansion happened, exhaust happened, suction happened. Okay, when the piston was moving from TDC to BDC, top dead center to bottom dead center. Okay, so that is where we say as the piston moves from TDC to BDC, expansion starts. Okay, then the expansion ends. When it ends, expansion starts when the combustion happens and the gases starts applying the pressure on the crown of the piston. Expansion ends when it ends, because when it comes over here, up to that expansion is happening. Whenever it moves and uncovers the exhaust port, what happens? Expansion ends, because further expansion is not happening. Why expansion is not happening? We have already discussed that whenever there is even a small passage for the gases to flow, the gases will flow through that particular passage towards atmosphere. Okay, now the gases inside is unable to apply the pressure on the top of the piston, and therefore we say theoretically the expansion has ended. Okay, this particular stroke has not been ended. See, stroke starting from TDC to BDC has not ended, but whenever it opens, the piston uncovers the exhaust port, the expansion has ended. Now the exhaust is happening when this exhaust port is opened. So the expansion ended, then exhaust happened when this was open, then the suction happens when the transfer port became open, and finally piston reaches BDC. So this is what generally happens when the piston is moving from top dead center to bottom dead center in case of a two-stroke engine. Now moving ahead, let us discuss what will happen when the piston is moving from BDC to TDC. That is bottom dead center to top dead center. So now we are saying the piston is at bottom dead center and it is going to move up. What is happening now? Suction is going on. Suction is going on. Exhaust is going on. Okay. So suction is going on. Exhaust is going on. Both are there. So piston is presently at BDC and it is going to move up. So piston starts moving up. Piston start moving up until it reaches over. Still this port is open and therefore suction is going on. Whenever this point reaches over here at that particular point, your suction is going to stop. So suction ends when this reaches over here and this has been closed. Okay, so when this particular port is being closed, the suction ends, but still exhaust is going on. Only the suction has ended, exhaust has not ended. Now further it moves, even when it moves and now it closes this particular port, exhaust also ends. Okay, exhaust also ends, and when it ends further from here to as it moves upward, then what happens? The compression is going to happen. So as it moves from this particular point to TDC, that is top dead center, we call it as a effective compression. Okay, so the effective compression is this much, and we have earlier discussed that the effective expansion was this much from TDC to this point, and effective compression is from this point to TDC. Okay, so therefore the unlike in a four-stroke engine where one complete stroke from TDC to BDC it is available for compression or for expansion, in a two-stroke engine the effective compression stroke and the effective expansion stroke is very less, and therefore power produced is less. Okay, so theoretically speaking, the power produced by a two-stroke engine will be lesser than a two-stroke engine per cycle. Correct? Why? Because the effective strokes are lesser. Which effective strokes? The expansion stroke, which is supposed to be the work producing stroke, isn't it? Since the effective expansion stroke is from TDC to this point only, but when the piston is moving from TDC to BDC, but only this much part is only the effective stroke. That means during this much part motion of the piston only, the pressure is acting on the piston, and therefore the net or the effective stroke is less, and therefore power output is less, and since the output is less, the efficiency of a two-stroke engine is comparatively lesser than a four-stroke engine. So here we are discussing about what is happening when the piston is moving from BDC to TDC. So initially the piston was at BDC. At that time exhaust was happening. The suction was also happening, or so suction to the combustion chamber was also happening. Now as it moves up and closes, here the exhaust ends, and here the suction ends. Here as it closes the exhaust port, suction also ends, and further from here to top dead center the compression is going to happen. So summarizing, and finally piston reaches TDC. So summarizing what is happening when the piston is moving from BDC to TDC, the suction was happening, it ends after some time. The exhaust was happening, the exhaust ends after some time. Then the compression starts and the compression ends and the piston reaches TDC. So summarizing, we said that as the piston is moving from top dead center to bottom dead center, the expansion, then the exhaust and the suction happening, and when the piston is moving from BDC to TDC, then the suction ends, then the exhaust ends, and then the compression starts and compression ends. So this is what we discussed. So basically, this was what is supposed to be happening when the piston is moving up and down in case of a two-stroke engine. So now let us move on to moving ahead, discuss about a four-stroke engine. Okay, so till now whatever we discussed was about a two-stroke engine. Now let us move ahead to discuss. I hope before moving ahead, can I make it open for doubts? So, is anybody having any doubt in the last session, whatever we have discussed? Working of a two-stroke engine? Anybody, any doubt? Please unmute yourself and ask. Anybody?
No,
No doubts? Okay. Okay, so Kedar is saying no doubt. So I presume that nobody is having doubt. Everybody is clear with this concept of working of a two-stroke engine. Still, anybody feels having a doubt, please unmute yourself and stop me and ask the question or whatever doubt you are having. Okay, so now let us move ahead. So we are going to discuss about a four-stroke engine. Now, these are the things again what we have discussed in the nomenclature part, engine nomenclature part, where we discuss this is a bore, which is the diameter of the cylinder hole. Then this is your piston. We have the piston moving from TDC to BDC. So the piston, so this was your piston. Whatever is a piston, piston is moving from TDC to PDC. The distance traversed is what you call as a stroke, and corresponding volume is what's called as a swept volume. And when the piston is at top dead center, whatever is the volume on the upper side of the piston in the cylinder, which we call as the combustion chamber, is called as the clearance volume. So this is your clearance volume, and this is your swept volume. Okay, and this is your stroke length, this is your TDC, this is the PDC, and the bore. So top dead center, as we already said, it is also called as outer dead center. Bottom dead center, so top dead center, it will be called in case of a vertical engine. If it is a horizontal engine, it will be outer dead center. Bottom dead center here, it will, this is a here, and it will be called as the inner dead center in case of a horizontal engine. You know, vertical engine, it will be bottom dead center. Then we have a stroke. Stroke is the distance traversed from one dead center to another dead center. Bore. Bore is the diameter of the cylindrical hole of the in which the piston is going to be accommodated. Clearance volume. Clearance volume is the volume above the piston when the piston is at top dead center. Swept volume. Volume swept by the piston when it is moving from one dead center to another dead center is called as swept volume. Okay. So knowing this much, and we have already learned. Actually, you know all these things. We are just it. You know that there are four processes happening to complete one cycle. That is the intake, compression, or suction, compression. Then we have the expansion of power stroke and exhaust stroke. Okay, so there are four strokes happening, and correspondingly Here it is shown initially the piston is moving down, then the compression it has to move up, then when the ignition happens during the power stroke it has to again move down, and during the exhaust it has to move up. Correspondingly, 4 strokes are there and 4. So you can just observe the position of the piston and cylinder arrangement. So initially it was moving down and it reaches the bottom dead center, then it starts moving up. So you can see it has started going up and it will go down, sorry, up, it will reach up, and the power stroke starts when the spark happens and it starts moving down again, and again reaching the BDC, it will move up for exhaust. So these are the 4 things supposed to be happen. And with respect to this, let us discuss the PV diagram of a 4-stroke SI engine. Okay, this is also called as the auto cycle. We have what you are learned in your first year. Okay, so you are well versed with this particular concept of auto cycle. We are going to revise it once again. Basically, how we are getting this. So basically, this auto cycle is also called as a constant volume cycle. Okay, it is also called as a constant volume cycle, and we are going to discuss what are the things which are going to be there in this particular cycle one by one. This process are we are going to discuss. Okay, it starts from here 0 to 1, and then from 1 to 2, then from 2 to 3, from 3 here to 4, 4 to 1, and 1 to 0. So this is a complete process. Okay. Now this is about the practical cycle. This is about the practical cycle. When you draw a thermodynamic cycle, you will be drawing from here. There will not be the 0, 1 part will not be included here. 1, 2, 3, 4, 1. This will be only drawn. Okay. So this we call as a theoretical auto cycle. Okay, theoretical auto cycle. Now, how we are getting this? How we are getting this, and what these lines are? Okay, so we should understand and how we are getting these particular lines. Okay, in order to understand that, we have just now discussed in the previous cycle that initially when the piston was at top dead center, and when it is moving down, the inlet wall is opened, and whenever the inlet wall is opened, the mixture is going to flow in. Correct? So the mixture is going to flow in. So when it is flowing in, remember that there will be some pressure which is making the mixture to flow in. So what is the pressure outside? Outside it is atmospheric pressure. So the suction is happening at atmospheric pressure. So here we have a PV diagram. So and the pressure we are denoting on this particular axis, and on this axis we are putting the volume. So we have it P, that is the pressure, and V, that is volume. So on the PV diagram we are denoting by some lines, and we are saying this so and so process is happening, and we'll see how this particular lines we are getting. Already you have learned, as I said, you have learned all these things in the first year DME subject, I hope. So there you have learned all these things, but still let us discuss once again, revise once again what is happening. Now to understand better, I have drawn here the cylinder and correspondingly the piston. So this is a piston correspondingly when the piston is at top dead center, and the piston correspondingly when the piston is at bottom dead center. Okay, so four operations happening are suction, compression, then we have expansion, and then exhaust. Expansion is also called as power stroke. Okay, so suction, compression, expansion or power, and exhaust. These are the 4 processes which are supposed to happen, and when this particular 4 processes happen, our cycle is going to get completed. So we should understand how this particular cycle is happening, and how we are getting this particular PV diagram. So 0 to 1 and 1 to 0 are inlet and exhaust. So 0 to 1 is the inlet process, and during inlet what is happening? During inlet the piston is moving from TDC to BDC. So initially considering that piston is at TDC, so this this particular line we are putting on the volume. Okay, so this is the top dead center line. Okay, line corresponding to the upper part of the combustion chamber, and this is the top dead center line. So here this much is the volume. So this much is your clearance volume. Okay, so this much volume is your clearance volume. Okay, and the volumes starting from TDC. So the piston starts moving from here. So from zero, which is a zero position corresponding to TDC of the piston now, and the piston starts moving. Therefore, the volume increases. Volume inside the combustion chamber or the inside the engine cylinder is going to increase. So it is increasing as the piston is moving from TDC to BDC. How until what? Until piston reaches BDC. So the volume is increasing. So volume initially it was from this clearance volume. Now suction. During suction, the piston has moved in this direction and it has reached over here, BDC. Okay. Now this is happening at what pressure? Atmospheric pressure. So PA, atmospheric pressure. On this line, we are denoting atmospheric pressure. So everything is happening, the suction is happening at atmospheric pressure. So there is no change in the pressure. Pressure is continuously atmospheric. So here, at atmospheric pressure, the suction is happening and the piston is moving from 0 to 1. So the pressure remains atmospheric throughout. Therefore, it is a horizontal line now because this is a axis on which we have put the pressure. So since the pressure is not changing, it will not go up or down. If it goes up, it means pressure has increased. If it goes down, it means pressure has decreased. But since the pressure is not increasing nor decreasing, the line become horizontal. That is 0 to 1 is a horizontal line. Okay, starting from here, which corresponds to TDC, and end here, which corresponds to BDC. So I hope everybody understood 0 to 1 line. So 0 to 1 line corresponds to suction process. During suction, what happens? Negative pressure is created inside the combustion chamber. Okay, as the piston was moving up, and so we have seen here. So as the negative pressure is created and the wall, the inlet wall is open, what happens? The negative pressure over here and the positive pressure outside will make the gases to flow in, because the fluid always flows from a high pressure region to a low pressure region. So the mixture starts flowing in. So the mixture is going to flow in. Okay, but even though the mixture is flowing in, the pressure is not increasing, because whatever the vacuum is being created over here, negative pressure is going to be created over here, is being occupied by the new mixture coming in, and therefore the pressure inside the cylinder, we can say, assume that it is going to remain constant, and therefore we have drawn a line 0 to 1. Any disturbance? Any disturbance? Yes. Any doubt? Anybody? Anybody having any doubt? Please ask if you have any doubt. Hope you are understanding what is being explained. Okay. So moving ahead. Now, so let us start. So this was the engine nomenclature, what we have discussed, and this in this particular slide, we'll go back. Okay, it's not coming. Okay, so 0 to 1. 0 to 1 was your suction stroke. Okay, so during suction stroke, we have got one line, 0, 1 line, correct, which is a horizontal line. Why it is horizontal? It horizontal indicates that pressure is not going to change, correct? Always the pressure is remaining atmospheric, and the piston reaches BDC. Okay, so when the piston reaches BDC, what happens? Initially, when this was moving, as we said in the previous slide, we have discussed, here the inlet wall was open. Okay, when the piston reaches BDC, this wall is closed. Already this wall is closed. That means in the next stroke, both the walls are going to remain closed. Okay, so now both the walls are remaining closed and piston is at BDC, and piston starts moving from BDC to TDC. So piston starts moving from BDC to TDC. So this was the step volume indicated denoted by PS. So when the piston is moving up, what happens? Whatever the gases are being, the mixture is being trapped inside is getting compressed. That means the pressure is going to increase. So we can see over here, the pressure line cannot remain now like this. But when the piston is moving from BDC to TDC, it has to move up. It is slowly rising. So as the piston is moving more and more towards top dead center, more and more the pressure line is going to move up. Okay, and it will reach over here when the piston is reaching top dead center. Okay, and this particular process is what we call as compression stroke. So line 1 to 2 is your isentropic compression process. So hope you are well versed with the word isentropic. So in isentropic process, entropy remains constant. Okay, and here the pressure is being increasing. So this particular pressure increase is being denoted by on the PV diagram. So you can see over here the volume is decreasing. Okay, from BDC to TDC the volume is decreasing. So if I take this much, the volume is now here. The piston was supposed to be here. When I reach over here, the piston is here. When I reach over here, the piston is up here. Okay, so as the piston moves from BDC to TDC, the volume is decreasing. That means this line will move towards this side. When the volume was increasing, it was moving toward this side. When the volume is decreasing, it has to move toward this side. So it is moving toward this side, but the pressure is increasing. That is why it is moving to upper side. So due to a decrease in volume, it is moving towards left side, and due to increase in pressure, it is moving towards upper side. And that means this becomes now a curve. And this curve goes on like this, and as the pressure increases till what? Till piston reaches top dead center. So now we have completed two strokes. Which was the first stroke? First stroke was TDC to BDC when suction was happened. So 0 to 1 suction happened. Correct? And 1 to 2, what happened? Compression happens. So the compression process, isentropic compression process is happening during 1, 2. Okay? Process 1, 2. And this is a curved line. So the curve indicates this particular curve indicates that pressure is increasing and volume is decreasing. So the arrow indicates it is moving in this direction. It means initially the volume was higher. When it comes to here, the volume was minimum. Here the volume was maximum. Here the volume was minimum. Here the pressure was minimum. Here the pressure was maximum. If you compare this line. Okay. So what was the pressure here? It was atmospheric pressure. And what is the pressure over here? Corresponding to this, some value will be there, where it corresponds to the compression ratio. Okay, so at the end of the compression ratio, initial volume is corresponding to 1, final volume corresponds to 2, position 2. Okay, so volume corresponding to this divided by volume corresponding to this, that is initial volume, this is the total volume of the cylinder, divided by the clearance volume will be your compression ratio. Okay, so the compression is corresponding to compression ratio. Some amount of pressure rise is going to be here, and that is value, this value. Okay, so depending on what pressure you want at the end of the compression stroke, you have to design the dimensions of the piston and the cylinder in such a manner that it is going to increase the pressure in that manner. And finally, when the piston reaches that TDC position, we should get that particular pressure. Okay, so that is our aim. Now I hope you understood this particular two strokes. Okay, stroke 0 to 1 and 1 to 2. That is the process. One process was 0 to 1 was suction, and 1 to 2 is compression. Now further, now the piston is supposed to move back. Okay, towards TDC. It will move from TDC to PDC further. Okay, but in between we assume that momentarily when the spark is going to happen, so we say theoretically at the end of the compression stroke the spark is going to happen. Okay, so theoretically we assume that at point 2 spark is going to happen, and when the spark is going to happen, instantaneously the mixture is going to burn. Instantaneously, the word instantaneously is very important over here. So we assume that instantaneously the mixture is going to burn and pressure is going to be developed. Why? Because the liquid or the vapor fuel, fuel in the form of a vapor which was there in the air fuel mixture is now getting burned, and due to the chemical reaction happening, this particular vapor, fuel vapor, is being converted into different gases. And now suddenly the pressure has increased, and this is happening instantaneously. So instantaneously means without any time, okay, or very short amount of time, negligible amount of time. So instantaneously the pressure is increasing due to combustion process. So we denote the increase in the pressure by moving upper side, correct? So here we have moved towards the upper direction until when the pressure is maximum. So here we say maximum pressure has reached, and due to what? Due to combustion. And theoretically we call it as a heat addition process. Heat addition process, which we say it is a combustion process. So thermodynamically it is called as heat addition process, because we have added the heat, or heat was not there initially and now the heat is over there. So in that sense it is called as heat addition process. Or here in practical sense it is combustion. So due to combustion, what happened? From 2 to 3 we have the process constant volume heat addition process. Volume is constant. Why? Momentarily, instantaneously the combustion is going to happen. In no time, the combustion is happening in a very small, very small, negligible amount of time. So there is no motion of the piston during that. Okay, instantaneously the pressure is increasing from 2 to 3. So we say it is a constant volume. When it is at TDC, what we said? What was a TDC? We said that dead center is that which we say it is going to piston is going to be remain momentarily stationary, correct? It is called as dead center, and here now the piston is at dead center. Okay, so when the piston is at dead center, and when the piston is at dead center stationary, at that time the combustion is happening and the curve is moving from 2 to 3. So what is this 2-3 line corresponds to? 2-3 line corresponds to combustion process. Thermodynamically it is called as constant volume heat addition process. Okay, now heat addition process, because earlier there was no heat inside, now the heat is there. Why the heat has appeared? The chemical reactions corresponding to the burning of the fuel has taken place, and the liquid fuel has been converted into gases. Okay, and therefore the heat has increased. Now due to this particular heat increase, so the what it means is that this particular reactions are exothermic. What is exothermic? Reactions in which heat is liberated is called as exothermic. So the combustion reactions are exothermic in nature. So during this particular reactions, the heat has been liberated, and therefore whenever this reaction happens, which is happening in this particular case at constant volume, okay, when the piston is at TDC stationary, suddenly the volume increases. Sorry, the pressure increases. Volume remains constant. Volume is same. At TDC only it is there, but the pressure has increased from 2 to 3. So we say here constant volume because the piston has not moved, and heat addition process because the combustion has happened and heat has been added, or the temperature of the gases has been increased. So now we have 3 lines. 0 to 1 was the suction, correct, during when the piston was moving from TDC to BDC. Then 1 to 2, the piston was moving from BDC to TDC, that was the compression stroke, wherein whatever the trapped gases was there, that has been compressed, and therefore pressure was increasing from here to here and volume was decreasing, correct? And this, without any change in volume, constant volume, we are able to increase the pressure. Why? Because heat is added. So due to the combustion, heat has been added, and due to the addition of the heat, the pressure has been increased from 2 to 3. So the process 2 to 3 is the combustion process or constant volume heat addition process in case of a Otto cycle. So it is 2 to 3. So 0 to 1 suction, 1 to 2 is the compression, and 2 to 3 is your constant volume heat addition process. Okay, now we have reached the point 3, which is corresponding to maximum pressure point. So this is the maximum pressure point. Okay, here the maximum pressure has reached. Now piston starts its motion from TDC to BDC. So when the piston starts moving, what happens to volume? Volume goes on increasing. So the volume is increasing. So the volume is increasing means the line should move towards the right. Okay. So it is moving towards the right side. Okay. Towards this side it has to move. But what is happening to pressure? Due to the increase in the volume, the pressure inside the combustion chamber is decreasing. So when the pressure decreases, the line has to come down. So now it is a curve went towards down, went towards down. So it is a curve now. It is moving towards down. Why it is moving towards down? Because the pressure is increasing. Why it is moving towards the right? Because the volume is increasing. Because we are plotting pressure and volume. So the volume is increasing on this side, the pressure is increasing on this side. That means when we indicate the pressure decrease, we have to increase in the lower side, that is decreasing pressure. Volume is decreasing, this will be towards this side, and when the volume is increasing, it has to be denoted towards right side. Okay, so here volume is increasing, that means it has towards move towards right, and pressure is decreasing, that means it has to move towards down. Therefore three lines starts moving down towards right. So this curve reaches over here when the piston reaches bottom dead center. So this process we call as expansion process. So during expansion, what is happening? The burned gases are applying the pressure on the piston and making the pressure to move from BDC to TDC. Sorry, from TDC to BDC. Okay, so from TDC to BDC it is moving, and therefore this line goes like this, which indicates the pressure is decreasing and the volume is increasing. Now we reach over at point 4 when the piston is at BDC. Now what is the further stroke remaining? So we have discussed initially that we have something called a suction, then we have compression, then we have expansion of power stroke, and then we have exhaust. So now we have here exhaust stroke. Okay, so now during the exhaust stroke, here initially itself we have said that 0 to 1 is your exhaust. 0, that is 1 to 0 is your exhaust. 1 to 0 is your exhaust. 0 to 1 is your suction. So now 1 to 0. But in order to move from 1 to 0, first it has to reach 1. But now we have reached up to only 4. And what is this 4-1 process? The 4-1 process is constant volume heat rejection process. That is similar to what we had did during the combustion. That is, momentarily we are assuming that combustion is going to happen and all heat is going to add it up, and suddenly the pressure is going to increase from 2 to 3. Similarly, we assume, underline the word assume, we assume that heat is being rejected instantaneously, and since heat has been rejected, the pressure decreases from 4 to 1. 4 to 1. Okay, so since the pressure is decreasing, it is being denoted by moving towards lower side. Okay, so in this side the pressure is increasing, pressure is decreasing on this side. So it has pressure is decreasing, but volume is constant, because this is happening momentarily when the piston is at bottom dead center. So instantaneously at constant volume, the rejection of the heat is taking place. So the line is moving down. Okay, so that is your 4-1. Now, is there something like this 4-1 process happening in actual cycle? In actual cycle, there is nothing like heat rejection process. Okay, heat addition process, combustion was there, is there in a actual cycle, because the combustion is happening. But there is nothing like a heat rejection process in actual cycle, in practical cycle. Then where this line comes from? So you know that whenever we are going to exhaust, we have to from 1 to 0, correct? And at that time, the pressure is going to remain again atmospheric, because the instant when you open the exhaust port or exhaust valve, suddenly the pressure reduces to atmospheric and all the gases starts moving out. Okay, instantaneously it is moving out. Okay, so rather it will be moving out, so it will be pushed and ensure that the pressure is going to be remain atmospheric. That means here the pressure was somewhat higher, this value. From here to, we have to make it reach over here, and for that we have added one line extra over here. We have assumed one extra process which is not there actually, which we say heat rejection process. Now, why we have added this? If you remember the concept of a heat engine, initially itself we have said that what is a heat engine? Heat engine, it is a device which takes some heat from the high temperature source, and small part of it will be heat rejected to a low temperature sink, and the remaining part is going to be converted into work. Correct? So that was the definition, how we discussed initially heat engine. So there was, and the last part of that particular statement, we have said that heat is rejected to sink. Some small amount of heat is rejected to sink. And we said that unless the thermodynamic principle tells us that without giving some small amount of heat to the sink, we cannot develop work. So here we have that particular process added over here. So this is an imaginary process added in the cycle. So if it was, say, if this exhaust was to happen, then we should have considered this line from here, like this. But again, it will be wrong, because these things are happening at constant, at atmospheric pressure. Why this is happening? Because now suddenly we are opening the valve, and due to the opening of the valves, this pressure is going to be reduced to atmospheric. So in order to account for that, we have added one imaginary process over here, which is the heat rejection process, and brought the curve from 4 to 1. But remember, in actual process, there is nothing like 4 to 1 process or heat rejection process actually happening inside the combustion chamber of a IC engine. Okay, and we say thereafter, that is from 4 to 1. So 4 to 1 corresponds to constant volume heat rejection process. Constant volume. So volume is remaining constant. Why? Piston is at BDC. Heat rejection process. So heat is rejected to low temperature sink. Now what happens when the heat is rejected? Pressure. What happens to pressure? Pressure comes down. Here we added the heat, suddenly the pressure shooted up. Here we remove the heat, suddenly the pressure comes down. So suddenly the pressure comes from 4 to 1. Okay, and from 1 to 0, it is exhaust process. And during this 1 to 0, the piston is again going to move from BDC to TDC. So as the piston is moving from BDC to TDC, what happens to volume? Volume decreases. So line starts moving in this direction. So as the line is the volume is going to decrease, the line is going to here. But is the pressure increasing? No. Is the pressure decreasing? No. So the pressure is going to remain atmospheric, and therefore at a constant pressure, which is corresponds to atmospheric pressure, the piston is moving from BDC to TDC, and we assume that inside the combustion chamber, atmospheric pressure, sorry, the pressure remains to be atmospheric pressure, and therefore we have drawn a line which is horizontal, which indicates that pressure remains atmospheric. So, sorry, constant, and the value is corresponding to atmospheric pressure, and the line is moving from right to left, so it is indicated by this arrow. So your 1 to 0 is your exhaust process, and that completes your cycle. Okay, so this is your PV diagram for a spark ignition engine, which we call as Otto cycle. Okay, so as invented by the scientist Otto, it is called as Otto cycle. We have discussed this earlier. So this is your Otto cycle, and it has 4 processes happening as we discussed earlier. That is suction, compression, then expansion, and exhaust. And which are they? These lines. So suction corresponds to 0 to 1, 1 to 2 corresponds to compression, 3 to 4 corresponds to expansion, and 1 to 0 corresponds to exhaust. Now in between, which lines are remaining? This line and this line. What this line corresponds to? This line corresponds to constant volume heat addition process, which is happening, which is assumed to be happening when the combustion happens inside the combustion chamber. And this, we assume that it is happening at constant volume. That is when the piston is at top dead center. So we are assuming here that all the combustion process, the complete combustion process is happening in a very negligible amount of time, correspondingly when the piston is at top dead center. Similarly, we have also assumed one extra process, which we say is a heat rejection process, which is again we are assuming happening when the piston is at bottom dead center, and correspondingly we have added this line. So in all, now we have 0 to 1 is your suction, 1 to 2 is your compression, 2 to 3 is your constant volume heat addition process, 3 to 4 is your expansion process, 4 to 1 is your constant volume heat rejection process, and 1 to 0 is your exhaust process. So this is what you call as Otto cycle. Okay, this is your theoretical Otto cycle. But remember, as I told you earlier, when you draw an Otto cycle PV diagram, you start from 0 to 1, 2, 3, 4. You will not draw this particular line 0 to 1. Okay, so 0 to 1 line or 1 to 0 line. Actually, there are 2 lines over there. Okay, overlapping on each other. So there are 2 lines. These 2 lines we are not drawing, and we say your cycle is this 1, 2, 3, 4. Okay, because we know that according to thermodynamics, we want a closed cycle. And if you keep it here and you move over toward this side, here it will be going to end. But when it is end over here, it is going to remain open. And we know that we cannot analyze a open cycle. So rather it will be difficult. Okay, since it is difficult to analyze a open cycle, we are going to convert into a closed cycle. Now, what will happen if it is converted into a closed cycle? Now we can go for thermodynamic analysis. So it is amenable to analysis when it is a closed cycle, and it is difficult to analyze when it is an open cycle. And therefore what we do is we convert an open cycle into a closed cycle by adding extra process 4 to 1, which is we are calling as constant volume heat rejection process. Okay, that is why 4 point has reached up to 1, and then it has moved like this. Otherwise this point would have moved like this. And here, so it was this here 4, and here it might be some 0.5, and from 5 to 0 nothing, because nothing is happening over there, because next cycle is happening starting at 0. So this would not be a closed cycle, but we want a closed cycle because we want to analyze it. Thermodynamic analysis has to be made possible. So in order to make it amenable for thermodynamic analysis, we had added one extra process which we call here constant volume heat rejection process. And now, since it is a closed cycle, it is amenable for analysis, or we can go for thermodynamic analysis of a closed cycle. Okay, therefore, theoretically speaking, our Otto cycle, when we draw, it will be 1, 2, 3, 4, 1. We will not draw this particular part because it is not included in this particular closed cycle part. Okay, so this is your suction and exhaust is not a part of your thermodynamic process as such. Okay, this is your practical process where the gases are coming in and gases are going out. When we say it is a closed cycle, we assume that it is a closed cycle. That means the working fluid is not going out and no working fluid is coming in. Fluid is not crossing the boundary is what is our assumption in thermodynamic cycle. Correct? But here, actual practical cycle is different. It is an open cycle because it is not closed. Every time, every cycle, new mixture is coming in, and at the end of the cycle, the bone mixture is going out. But in order to make it thermodynamically amenable to analyzable, what we have did, we have converted the open cycle into a closed cycle. How do we have did that? We by adding one imaginary process. And which is that process? It is the process 4-1. What is the name of that process? It is constant volume heat rejection process. Okay, now your thermodynamic cycle becomes 1, 2, 3, 4, 1. It is a closed cycle which can be analyzed thermodynamically. Correct? And 0 to 1 is your suction and 1 to 0 is your exhaust, which is not a part of as such a part of a thermodynamic process, because according to thermodynamic cycle, closed cycle, the working fluid should not cross the boundaries. Okay, so this is your boundary, correct? This is your boundary, and this boundary should not be crossed. But it is happening. Here we have an inlet port, here we have an exhaust, correct? So here we have an inlet port through which inlet is coming, mixture is coming. Here we have an exhaust manifold through which exhaust gases are moving out. Okay, so the mixture is fluid is coming in and going out every cycle. But thermodynamically, we assume that fluid is not crossing the boundary, but it has to cross the boundary, and therefore the 0 to 1 and 1 to 0 is not a part of, it is not becoming a part of actual thermodynamic process when we assume it for analysis. So this becomes your actual, theoretical Otto cycle 1, 2, 3, 4, 1, which is a closed cycle. And this is the extra lines 1, 0 to 1 and 1 to 0, which corresponds to inlet process and exhaust process. That is suction and exhaust. So I hope everybody has understood. Everybody has understood the suction, the compression, the constant volume heat addition, the expansion, heat rejection, and exhaust process. Now, I open the session for questions. So, is there any doubt related to whatever has been discussed? You can unmute yourself and ask your doubts related to Otto cycle, whatever we have discussed now. So, this is your Otto cycle. The PV diagram, whatever we have drawn, is for Otto cycle. So, now, any doubt? Please unmute yourself and ask your doubts. I'm waiting for questions. Or else you can put your doubts in the chat box. I can read it from chat box and give the answer. No problem. Any doubts? Anybody having? Otto cycle. Till now, whatever we have discussed. Anybody having any doubt? So as I always tell you, there are no questions. means two things. One, everybody has understood everything and nobody has understood nothing. So please ask. Is everybody awake? At least let me give that one confirmation through chat box, or unmute yourself and say yes, sir. We are awake.
Yes, sir.
You are awake. Okay. So Pramod, everything clear? Pramod Avlekar, everything is clear. May I ask question? Can you unmute Karande, Gaurav? Can you unmute yourself?
Yes, sir.
Any doubt?
No, sir.
So you tell me what is this process 4 to 1?
Which one, sir?
4 to 1 process.
4 to 1. Yes, sir. This is it is a heat rejection process.
Okay.
After spark plug ignition plug, the fuel get burned, and these burn gases outcomes from the exhaust valve.
Heat rejection, where see, burned gases flowing out is from here to here. Then when you said about combustion, that is happening over here. What about this 4 to 1 process I am asking? I want specifically 4 to 1. What is happening? Guru, what happened? Yes. Once again, unmute. Guru.
Yes, sir.
What about 4 to 1? You tell me. I am asking about the process 4 to 1. What is the process 4 to 1? Okay. Anybody else? Pramod, can you tell what is the process 4 to 1? Pramod Avlekar. Pramod Avlekar, can you mute yourself? Unmute yourself and tell me. Can you tell me what is the process 4 to 1? Pramod? Yes. Abhijit? Abhijit Kukre? Can you unmute yourself and tell me? See, you have to respond. Abhishek, Jodmote. I'm calling the names. Nobody is responding. Diksha Admile. Diksha Admile. Diksha Admile. Can you unmute yourself?
Yes. Yes, sir.
Please explain what is process 4 to 1.
In that, sir, assume that heat is released and
so when it is happening? Actually, when it is happening actually?
4 to 1.
4 to 1. So see, as we said here, the combustion is there. Something is going. We know the fuel is going to burn. Here, what is happening? In actual engine, here we said heat is being added. At that time, we are knowing that the fuel is burning. That is where we are adding the heat. Here, what is actually happening inside the engine during process 4 to 1? Diksha?
Volume constant.
Volume constant आहे, पण नक्की काय होतं त्यावेळेला? Tell me what is happening actually.
Heat rejection.
Heat is rejected from where to where?
4 to 1.
Okay, see here when we say heat is added, we are saying that heat is added to gases. Earlier it was at a different temperature. Now due to combustion process, heat has increased. Is there happening something like this here? Diksha? Is there something happening like that? Kunal Shetty, can you unmute yourself? Kunal,
Yes, sir.
tell me what is 4 to 1?
Yes, sir.
What is 4 to 1?
Heat is rejected to surrounding.
Heat is rejected to surrounding. How it can happen with before the exhaust is going to happen? Still the gases are inside the combustion
Yes,
chamber. Still the gases are inside the combustion chamber. How the heat is going to given out to the surrounding? Okay. So what I will do is once again I will revise. Okay. So I will revise once again this particular process, what is going to be there to make you clear. Okay. So initially I said, see, that is why I have drawn here combustion chamber, sorry, the cylinder and piston arrangement to make you understand what we are going to correlate the things. What actually is happening on what actually, practice, sorry, theoretically what is happening. Okay, this is a theoretical things. Okay, thermodynamics, and this is your actual thing. So actually when the piston is moving from TDC to PDC, what was happening? The volume was increasing, correct? Piston was moving from top dead center to bottom dead center. Volume increased, but the pressure remains constant. That is why here this was horizontal. Okay, so actually what happened? Actually piston moved from TDC to BDC. Okay, now here during 1 to 2 process, what actually happened? Actually piston move from bottom dead center to top dead center. Actually piston move from top dead center to, sorry, bottom dead center to top dead center. What happened therefore? Therefore the volume decreased. So the volume decreased. Okay, so this is line volume. Here on this side it is increasing, volume decreasing means this side. So the volume is decreasing, and correspondingly since the volume is decreasing and gases are trapped in a particular volume and that volume is decreasing, what will happen? The pressure will go on increasing. So the pressure is increasing. That is why the line is moving like this and reaches up to here. So the line reaches up to here. Okay, that is point 2. Okay, so in this portion, what was actually happening? Piston was moving from top dead center to bottom dead center. What is happening actually from here to here? Actually, piston is moving from bottom dead center to top dead center. Here, what is actually happening? Here, actually, combustion is happening. Combustion is happening. Okay, that is the mixture is burning. That is what is happening. But we are assuming everything is happening instantaneously, and therefore, since it is instantaneous, that means no time. That means it will not be moving. Okay, the piston is at same top dead center position, and since it is burning, combustion is happening, the heat is added. Heat is added means combustion has happened, the temperature of the gas has increased due to burning. Therefore, what happens when the temperature increases? The pressure also increases. So the pressure increased and becomes maximum. Okay, so what actually happened during the process 2, 3? Actually combustion happened. Actually combustion happened. Okay, and theoretically here the pressure has increased and the line is going like this. Okay, now maximum pressure reached over here and you are moving down. You are moving down from 3 to 4. What actually happened? Actually piston is moving from TDC to BDC. Okay, piston is moving from TDC to BDC. I have not taken the attendances. So many are leaving. Why they are leaving, I don't know. Okay, don't leave, because still there is much time remaining before the next lecture, and I'm clearing your doubt because I have come to understand that you are not understood. Okay, so 3 to 4, what is actually happening? Actually happening is piston is moving from TDC to BDC, top dead center to bottom dead center. What happens when the piston is moving from top dead center to bottom dead center? Volume is increasing. So volume is increasing. It has to move in right side. What happens to pressure? The pressure has to decrease. Why? Because the volume is increasing. Okay, so since the volume is increasing, it is moving towards right side. This is since the pressure is decreasing, it has to move down. So the line is moving like this. Okay, and reached up over here. Now the question, my question was, what is actually happening during process 4 to 1? Now can anybody tell? Sachin Sutar? Sachin Sutar? Unmute yourself and tell me what is happening. Tell me what is happening. Sachin Sutar. Or else I will assume that Sachin is sleeping. Please unmute yourself. Sachin Sutar. Okay, Sachin is sleeping. No problem. I will mark in absent. Sainath Kharade. So now Sachin directly left. Since I am calling, he is leaving. Oh, he's there, but he is not unmuting himself. Sainath Kharade. Unmute yourself and tell me what is actually happening during the process 4 to 1. 4 to 1. Yes, unmute. What happened? Again, you muted yourself. Please unmute yourself and tell me what is actually happening during the process 4 to 1. Pressure is volume is constant. Okay, and therefore, but what is actually happening inside the engine at that time? Okay, I will answer. Actually, that is where I said that there is no such process as heat rejection process happening actually inside the combustion chamber. But if we are not adding this particular process, then we have to consider 4-1 or 4-5 line like moving like this when the piston is moving from BDC to TDC, and at that time your complete process will be 0 to 1, 1 to 2, 2 to 3, 3 to 4, and 4 to 5. This will be your process, which is an open process. And since a process is open, it is not able to be analyzed thermodynamically. And therefore, in order to make it analyzable, analyze करण्यासाठी analyze करायला शक्य होण्यासाठी, okay, in order to amenable for analysis, what we have done, we had added an imaginary process, heat rejection process, and we have made this particular open cycle into a closed cycle. 4 to 1 is an imaginary process. Nothing in the engine is happening corresponding to line 4 to 1. It is not happening. Actually, nothing is happening like that. There is nothing in the engine happening during the process 4 to 1 where we have written heat rejection process. Nothing like that is happening over there. I hope everybody is getting, because this is a imaginary process which we have added over here. Since we have added this particular imaginary process over here, what we are able to achieve, we are able to make the open process into a closed process, or open cycle into a closed cycle. I hope you have learned open cycle, closed cycle in thermodynamics. Okay, so this now becomes a closed cycle. 1, 2, 3, 4, 1 becomes a closed cycle now. And what is why we have made it a closed cycle? Because now, since it is a closed cycle, what is a closed cycle basically? If the starting point and the end point is same, it is called as a closed cycle. Okay, so and why we go for making a cycle as a closed cycle? Because if it is a closed cycle, then we can analyze it. Okay, the analysis is possible only if it is a closed cycle. In order to easily analyze it, we have to convert the cycle into a closed cycle. So 4 to 1 is an imaginary process. Remember. So if you are asked what is actually happening during the line 4 to 1, the answer is nothing is happening corresponding to 4 to 1. It is the imaginary line what we have added 4 to 1 in order to make the cycle closed. Okay. Then we say from 1 to 0, it is our exhaust. It is our exhaust. Okay. So 0 to 1 is your suction, 1 to 2 is your compression, 2 to 3 is your constant volume heat addition. Now, is there anything happening during this? Yes, it is happening. What is happening? Combustion is happening. Combustion is happening. Okay. So what is combustion? Burning of these gases, mixture, fuel in the mixture, and this vapor getting converted to fuel, vapor getting converted into different burnt gases. So that particular chemical reaction was happening over here in actual, but we assume that it is instantaneous and therefore we call it as a constant volume. Here also we have assumed it, this is happening at constant volume. Though even though nothing has happened, we have assumed that it is a constant volume process, heat rejection process. Okay, and that is why it is, since it is a constant volume, the volume is not changing, and since it is a heat rejection, pressure is decreasing. Okay, so it is an imaginary constant volume heat rejection process, and nothing like this is happening actually in the cycle. But we have added this particular process 4 to 1 into the cycle in order to make an open cycle into a closed cycle. Why? The closed cycle we can analyze it. The open cycle, it is very difficult to analyze. Closed cycle is comparatively easy to analyze. So in order to amenable for make it amenable for analysis, we have added one imaginary process 4 to 1. That is the answer. I hope everybody understood what is being discussed with respect to cycle. Point 4 to 1, line 4 to 1. Can you give the confirmation that you have understood or not? Or you ask me doubt any once more? Yes, everybody understood everything? I want confirmation. Or again, I will start asking for the names and asking you to answer. Somebody give the answer. Unmute yourself and give the answer. Any doubt remaining? No doubt? No doubt? Okay, Pramod Avlekar, tell me when is the spark? Where is the point of spark? In this particular closed cycle, where is the spark given? Pramod Avlekar, unmute yourself and tell me spark point. At what point the spark is given? Which is the point at which we are giving the spark? Avlekar. So Avlekar is again sleeping. Sainath. Sainath Kharade. Once again. Sachin was sleeping. Kunal Shetty.
Sir, 2 to 3.
Which is the point of spark? At a particular point we are giving the spark. 2 to 3 is the combustion process, and combustion process happens after spark is given. So which is the point at which we are giving the spark? Yes, which is the point at which we are giving the spark? Point. Somebody has written Balaji Pise. So can you explain, Balaji? Can you unmute yourself and explain how it is at point 2 then?
When piston moves BDC to TDC, then
Correct.
pressure increases.
Correct.
That time spark plug is ignited spark, then high pressure condition is produced that time.
Okay, very good.
Then we get power stroke.
Correct. After combustion, we get the power stroke. Okay. So theoretically, very good. Balaji Pise, very good. So what is see? Generally, we say that at the end of the compression stroke, we give the Spark is ignited. Which is the compression stroke? 1 to 2. So at the end of the compression stroke means at the 1-2 process end of the compression stroke, that is at a point 2, we give the spark. And after spark, the combustion is happening. So 2 is the point at which we are giving the spark. Okay. So I hope you have understood the process of Otto cycle. So in a similar manner, I want yourself uh, to learn the Otto cycle and uh, explain. So the first question for your assignment number 1 is explain the diesel cycle with the help of a PV diagram. Okay. So the question for assignment number 1, I'm writing in the chat box. Explain the diesel cycle Vibhuti is entering now. Explain the diesel cycle with the help of a PV diagram. So this is the question number 1 for your assignment number 1. Explain the diesel cycle with the help of a PV diagram. So the way I have explained the PV diagram, so you should again draw a PV diagram, then the piston and cylinder arrangement, and initially you have to write the process 1 to what is your 1 to 0, 0 to 1, 1 to 2, all the process.
सर डिझेल सायकलची सायकल ही होमवर्क आहे. हॅलो.
Hello. Hello. Lecture संपलंय. अजित.
हॅलो. अरे अजित
बोल की. बोल.
झालंय बे लेक्चर.
झालं वाटतं, चाललंय.
तू घेतो का लेक्चर आता? हा, तू घेतो का लेक्चर? नको रे बाबा नको.
अक्षर तू घे, तू घे.
ठीक आहे तू.
अक्षर तू घे की.
अक्षय नंबर नंबर काय?
रेकॉर्ड चालू आहे.
अरे युट्यूबवरच घे.
गौरव
काय होत
पिक्चर
नाही
बघत बसलेला का? गौरव पिक्चर बघत बसलेला का? नाही काय तर पबजी खेळतोय म्हणून 4 to 1 विचारते, 1 to 4 विचारते. होय.
अभ्यास करा बे. ए अभ्या, तू पबजी खेळतो ना, मला अभ्यास कर म्हणतोय.
ते आपण डिलीट केली,
डिलीट केली ना?
सोडून दिलं आपण.
डिलीट केलं असं करला.
डीपी बदलला गेला. अक्षय
गौऱ्या एक काम कर की, अजून एक आपली
बोल
मीटिंग
की.
तयार कर. वेगळी लिंक तयार कर, आपण पोरं ऍड होऊयात. करे का ना आपल्या ग्रुपवर?
हा टाकतो.
हा 5 मिनिटात कर.
हा. साई कुठे गेला साई?
बहुतेक येत नाही सर. अरे 5 जण पण. लिओ हे अभ्या. पबजी आरसीबी.
There is a network problem in the college internet, therefore here I will stop our lecture. I will. ಹೇಳಲ್ಲ.
ಲೀವ್ ಆಗಲಿ ಗೌರವ್ ಇದು ಹತ್ತು ಡೌನ್ಲೋಡ್ ಲಿಂಕ್.
Tu viro